Hello everybody. We're finally done with section 4.2, which is an introduction to the node voltage method. We talked about node voltages versus terminal voltages. We introduced some terminology, things like the ground node, as well as what a node voltage is. We discussed the recipe and how to modify Ohm's law, and we saw an example of how to use the node voltage method in order to analyze a circuit with only independent sources. We now move on to section 4.3, and this is the node voltage method and circuits with dependent sources. So here this is the node voltage method. And circuits with dependent sources. Now, I'm going to show you how to handle circuits with dependent sources using the node voltage method through an example. And I'll show you guys that as we're going through the analysis, there does come a certain point at which we're stuck, right? But there is a workaround this getting stuck, right? So consider the following circuit. This circuit contains an independent current source providing us, wrote the direction of the current wrong. So it's providing us with 3 amps up this way. We then see a resistor down this way. Over on this branch, we see a resistor followed by a dependent source, like this. It happens to be a voltage source, so inside of here we have a voltage. And it depends on a current I delta. So it's 5 times whatever I delta is. And I'll show you where I delta is here in a second. We then have another resistor. And an independent voltage source providing us with 80 volts like this. And then the circuit is complete. This is a 200 ohm resistor. This is a 10 ohm resistor. This is a 20 ohm resistor. And the I delta that this source depends on flows in that direction through the 20 ohm resistor like this. Lastly, we need to know what we're looking for. There is a voltage across the 200 ohm resistor with that polarity, V0, that's what we're looking for. So here we want to use the node voltage method. To find the unknown voltage V0. And we're going to start where we did last time. So the first thing that we need to do is we need to identify the nodes and then select the ground node. Now notice that there is one large node here at the bottom, like this. There's another large node here at the top. It goes like this. There's a node there that's easy to miss, and there's one last node here that's extremely easy to miss. Notice that there's a node there because that is the interconnection between the dependent voltage source and the 10 ohm resistor. Now, I'm going to go ahead and select this node down here as my ground node. So I'm going to assign that a node voltage of 0 volts. And then we need to take a look at the voltage sources. So here there's a voltage source of 80 volts. Notice this particular polarity. And it's sandwiched between this node and that node. That means that this node up here is not independent. Now, in going from this node up through this source up to that node, we go through a voltage rise of 80 volts. That means that the node voltage at this node is 80 volts. Now, there is a second voltage source, and it's this one. Now, notice that in going from the reference node up to this node in question, we're going through a voltage drop of 5I delta. That means that the node voltage here, and you have to be extremely careful, is not 5I delta, it is minus 5I sub delta. Right? So the node voltage at that little tiny node here, this one, is minus 5I delta. There are no more voltage sources. That means that whatever nodes are left are independent nodes, and we have to give them a variable name. So here, one of the things that I can do is this node, I could give it a variable name, but notice that we already have a variable name established for it. So here, when I go from the ground node up to that node in question, I'm going through a voltage rise of V naught. Why? Because it has this particular polarity. So rather than giving it some arbitrary name like V1 or VA or whatnot, I am just going to say that that is going to be V naught. So let me redraw what I just erased. So this node voltage right there is V naught, and I'm going to call this node A. So I have now labeled my independent nodes. I'm now in a position to use KCL. So I'm going to use KCL at the essential nodes. Well, the essential node here is node A. And I'm going to add up all of the currents flowing out of this node. They must add up to 0. Remember, we are assuming that all the currents are flowing out of that node. So here we have, at node A, we have a current flowing out this way, current flowing down that way, current flowing down that way, and then a current flowing out that way. Now, this one is relatively easy to take care of, right? We have 3 amps flowing into the node, which means into KCL, as my previous example had showed, is we have minus 3 amps going in. Then we have a current flowing from this node down to the ground node through the 200 ohm resistor. That means that we have V naught minus the ground node over 200 ohms, like this. We then have this current, which flows from node A down to the ground, not to the ground node, but down to this node here through the 10 ohm resistor. So here we actually have plus V naught minus, and be careful, it's minus 5I delta over 10 ohms like this. And then lastly, we have this current going from there to there, and according to the modified version of Ohm's law, this is V naught minus the 80 volts divided by the 20 ohms, and all of that should add up to 0. Let me get rid of these supplemental highlights. Oh, got rid of more than what I wanted. Oop. Let me put that back. We still need that resistor there. And we still need this node. So this equation we want to clean up. So I'm going to multiply everything through by the common denominator of 200, in which case I get 200 times minus 3, that's minus 600. 200 cancels out cleanly and left with plus V naught. This minus sign, that minus sign gives rise to a positive sign. 200 divided by 10, that's 20. So we have plus 20 V naught, and then 20 times 5 I delta, that is 100 I delta. And then we have 200 divided by 20, that's 10, so we have plus 10 V naught, and then 10 times 80, that's minus 800, and then 0 times 200 is 0. So now we can actually gather like terms, right? Here we have 1 V naught, 20 V naughts, 10 V naughts for a total of 31 V naughts. Then we have 100 I sub deltas, so plus 100 I sub deltas. And then minus 600, minus 800, that's minus 1,400. I can add that to the opposite side to get 1,400, like this, and I'll call this equation 1. So this equation was obtained by using KCL at this essential node. Now notice, if you go back up here, what we did last time was we used KCL at another essential node to set up a system of 2 equations and 2 unknowns. We definitely have 2 unknowns. We don't know V naught, we don't know I sub delta. Where are we going to get a second equation to set up a full system of equations so that we can solve? Now, this incompleteness of the system of equations does come about because we have this dependent source, right? Now, this dependent source, which is right here, it depends on the current I sub delta, and I sub delta has been defined to be right there. So one of the things that we're going to do is to obtain another independent equation. This is a constraint equation. We look at what the dependent source depends on. So over here, what I'm going to do is I'm literally going to redraw that section that I'm boxing in. So that dependent source depends on I delta. I delta has been defined to be right here, and we're going to get another independent equation from there. So that I sub delta, there's a node. We have a resistor going to another node like this. This is at plus 80 volts. This is a 20 ohm resistor. I sub delta is flowing out that way. And we have defined that node to be at a node voltage V naught, and this is the node A that we had defined. So I'm just concentrating on this I sub delta. Everything else in the circuit I'm not really paying attention to. Now I can use Ohm's law, the modified version, that incorporates these node voltages to say that I sub delta is, well, it is the node voltage of where the current's starting minus the node voltage of where the current's ending divided by the resistance that it's flowing through. So here I have V naught minus 80 volts over my 20 ohms like this. And this is now my independent equation, but it's not in standard form. So one of the things that we can do is we can rearrange this to be in standard form. I can multiply everything by 20 ohms. So I get 20 I sub delta is equal to V naught minus 80 volts. I can move that over there and then move that over there, in which case I end up with V naught minus 20 I sub delta is equal to 80. This is in standard form. This is my equation number 2 now. So this equation we obtained by taking a look at the dependent source, what it depends on. We now have a system of equations in standard form. Equation number 1 was 31 V naught plus 100 I sub delta, and that was equal to 1,400. And the second one is V naught minus 20 I delta is equal to 80. And you can use any technique that you want to solve. My favorite technique is to throw into a calculator. So using a calculator, which I did previously, you will find that V naught is equal to 50 volts. And as an added bonus, that I sub delta is equal to minus 1.5 amps. And we have our solution. For the next example, one of the things that we're going to do is we're actually going to take a look at a circuit that contains what they call a supernode.